Uh, yeah. So, thanks a lot for being here. This week, we have Xiangxiang from MIT giving a talk on deep learning from an information perspective. This week, he decided to merge BLISS seminar with the machine learning theory group in a topic. So, yeah, please take over.
Yeah. Thank you for having me here. And okay. So if you cannot hear me, just let me know. Okay. Yeah, since I don't know how to work typically, but for this room, maybe it's fine. So the talk would be somehow try to understand deep learning from information perspective, and we need to take a different look at what we mention as like information is, and I'm glad of like BLISS in the middle. This I is like information supposedly, right? So we all know AI is everywhere, and there's a workshop I'm going about AI. But so this shows some traditional like manufacturing, even manufacturing and banking. You have this all AI tools, but this doesn't address everything. And if we think about it, a good counterexample you will see here is you can easily complain it doesn't address something we want to do, but on the other hand, do something we might not want it to do. So all of this is related to how we use data, what are the available data. And interesting thing is, if we think about some examples, we don't really know what is happening behind the AI. So that gets some security issues. And like if we think about driving, you don't want AI to take in charge. But if we think about it, how we address this, and the common solution seems very popular one is building larger and larger computation. So that gives you a sustainability issue, and people really worry about the energy consumption. That could be a thing. So instead of this, let's think about why this is so hard to understand, why we couldn't understand what's happening, why the thing is called a black box. The answer is easy, even for the things model. This is notably the easiest type model nowadays. So this is the classification. If you want the model to tell you this is coffee or espresso instead of a pizza, what you did is sorry about this. Kind of thing is not very good, but this is a convolutional neural net you would build. So what's happening is that after all these layers, you get some decision, and this is your estimation of the posterior, and it's espresso because the posterior is larger than a pizza. So the key difficult thing is if you look at the system, it's so complicated, there are so many parameters, and this is one of the few cases we could do visualization, but in most cases, visualization doesn't address problem if you think about large language model because you are living in a high dynamic space. So a key difficulty here is to understand how we extract the information from the data. And when we talk about information, it may sound very abstract because this is a very complicated system. So we would like to follow a lesson taught by Shannon. And what Shannon mentioned is it is first necessary to abstract things. So we have some mathematical concepts that's abstract from the reality. And for this picture, what we would like to do is have one abstraction that is, if we cut the box in the middle, then we will realize, though there are many complicated fancy operations in the middle, but eventually there's a function of your input data. So we call this as a feature matching, and we will just like to abstract this as a box like this. That gives us a view. We can think of what kind of feature learned by the network and get back what we want to learn. So, yeah, that's the thing. Anyway, yeah. So if we look at this figure, once we abstract this whole part as a feature, then we will find that we can have a simple block diagram that is from the data, that is the image label pair. We have a learning process that gives us a mapping. And if we look at the decision or the posterior, that's the model we learned, it's exactly by assembling the feature. So to be exact, what's happening is if someone told you what you learned here, and you look to the right, you find that's nothing but a regression model or softmax regression model. So that says, in this example, we could have understood this just as we learned something. And this seems to be a tool to get the posterior estimation. So there are several questions we like to ask. One is, if we think about the classification, we are using the feature structure as a tool, so you never see it. But without learning good features, softmax regression won't work. So one thing is, can we separate the two parts in the sense that we can learn some feature and assemble it for different tasks, so that we don't need to borrow a task to learn the feature. So to this end, the first thing we need to do is, can you check the chat? There's something.
Yes, it was just for audio train.
Oh, I see. Maybe let me do this. Okay, yeah, anyway. So the first thing we like to do is to see what's the information and how to interact with the deep neural network training. So I call this as the foundation. So we need to understand something, and to do this, we must convert to some mathematical problem. That's some X, Y problem. And for the previous example, you can just think of X as the input image and Y is the label you want to predict. And we ask the question, what kind of feature we want to learn? Suppose this k-dimensional feature. So if we think about the information perspective, what we want as a posterior py given X. And now we want to operate on feature space. So instead of having py given X, we now have the best estimation would be py given f of X. That's the information. And obviously, we don't want to lose any information, so that's a natural condition. We want to have the equality. And this kind of F, if satisfy this equality, it would be sufficient statistics. And you will find this is a bit tricky in the sense that if we do nothing, we have the equality. So information itself is not good enough. We want to have a more compact representation. That says, if we further process this F, we want to get the equality for any non-invertible mapping. So in short, that's asking something that's simple, but no simpler. That's the information sense. One thing we haven't discussed is we don't know how to compute this posterior. So let's get back to the computation perspective. The posterior py given fx has to be something about fx. Fx is like k neurons, k-dimensional stuff. And we like to have a feature structure to help us simplify the computation. That says, this cannot be another like 100-layer network. If you do that, then that doesn't make sense. So we go to the extreme. The same computation we could have, in a sense, would be linear. That is, you have apply some linearly. So you introduce k weights, and you get the weighted sum of this kf. So on the left, you have this posterior. On the right, you have this linear function, and you would notice that because it's a function of y. That says to predict different objectives. Let's just think about classification problem. Your w has to be a function of y. Otherwise, you won't get a meaningful result. So w depends on y, and w is k-dimensional. This is totally symmetric. We would like to rename this w as some g of y. Now we have a symmetric picture. One side we have f, the other side we have g, and both are k-dimensional. And if you check the inner product, we get this symmetric bilinear form, fx dot product with g of y. So the right-hand side is symmetric, and the left-hand side posterior, it is not yet. We just need to change it a little bit, so we convert this posterior to the symmetric form, which would be the density ratio. It's a natural choice. So on the left, that's the dependence between x and y as the density ratio, and the right, this is bilinear form. This would be the feature we want to extract. And the only thing we need to do is connect those two. So if we could connect the density ratio with this bilinear form, then we are done. And mathematically, we would like to go to a more standardized form. So if you just set quality here, then this would be a factorization problem. And we know a standardized or normalized form of factorization would be singular value decomposition. So we will do slight change to the left side and right side. To the left side, we just subtract 1 because this gives us somehow center result. We call this as I function, joint function of x and y. And why we can call this a dependence? Because we can see that when x and y are independent, we have this I vanishes. So in short, we can use this as a representation of the joint dependence. This is bivalent function. And to the right, instead of just have factorization, we could do singular value decomposition in the function space. And the sigma I and fi star, gi star would be singular values and singular functions in the space. So from the singular value decomposition, we can see this is normalized to be univariate and uncorrelated with different dimensions. And singular values are monotonically decreasing. That's the spectrum of the dependence. And one thing we would like to note is we can stack all the different dimensions, that's your different singular functions, and get F star and G star. This is multivariate or multidimensional features. Why we would like to focus on F star and G star? One thing as a sanity check, we could see that if we use the F star of X and G star Y as a feature here, we can accomplish the separation as we hope for. So if we first learn F star X and G star Y, because the density ratio can be fully expressed by F star X and G star Y. That says, if you want to predict anything about X and Y, you just need to apply linear adaptation. That's from the bilinear form.
What does the star mean?
Star is just to denote this is something. Yeah. I mean, if we don't do that, since later on we would use some F and G just as free variable. So this star will be the result you get from SVD. And you can think this would be optimal in what sense? In the SVD sense. Yeah. Sure.
So maybe we discuss it, but it's unclear like why the left hand side is a joint
function
on x and y.
Yeah.
Right hand side seems to be it seems to admit a linear separation between f and like x and y.
Yeah.
Completely separated.
But it's infinite. It's infinitely long.
Is that a trivial to see this always? Like,
I think so. Just imagine Taylor expansion. Just imagine it were just polynomials. You can always Taylor expand and then write it as a giant tensor of 1 comma x tensor p tensor infinity dot 1 comma y tensor p. And you can always write the Taylor series.
Yeah, that's a good comment.
So it's kind of a trivial.
So if you want to be more comfortable, just think about X has a kernelity of like 1,000 or 10,000. Y has a different kernelity, and this would become a big problem. And for the general case, it's SVD of Hilbert space, and the left side would be a joint function, and you are writing as a sum of a few autoproduct or rank 1 modes. So the sigma I could be going on infinitely, but it would decay in general. You just need to require the density ratio to be square interval. Yeah. So that's a good remark. I would like to say that F star and G star, they achieve minimum sufficiency in the sense that this would be the informationally optimal thing we want to pursue. That is, if you further process it, you lose something. But if you just keep it as, it gives you everything. So that's something we have defined. And good point is this anyhow like anything new? Actually, it's closely related to many classical statistical concepts. So one of this is the maximum correlation. And the formulation of maximum correlation is if you consider given x and y, I could find one-dimensional functions fx and gy to maximize their Pearson correlation coefficient. And turns out, if you do the optimization, the optimal normalized function you would get would just be f1 star and g1 star. And the optimal value would be sigma 1. This has a very good geometric interpretation, since by computing correlation, we are doing some kind of inner product. To be clear, if we consider feature space, we have x features and y features. And the maximum correlation problem becoming finding the principal vector and principal angle between the two subspace. So the sigma 1 will be the cosine angle just here. And we can continue this process because the feature space are high dimensional. So instead of just looking at the first pair, we'll get second pair by restricting them to be orthogonal, which is uncorrelated to first pair. Then we will get F2 star and G2 star. So if you recall that what's happening in the principal angle and principal vector, they are just the geometric meaning of singular value combination. Hope that gives you more comfort view. And they are also rediscovered or discussed in some different contexts. For example, as early as Pearson's contingency table, that's almost more than 100 years. And correspondence analysis is the same thing. CCA is a special case if you restrict the feature space to be linear. So that's the mathematically very classical stuff. And we will naturally think, okay, this has been here for such a long time. How do we compute them, or why this is not a thing in your standard package? The short answer is it's not easy to do the computation, and for obvious reason, you don't know the left-hand side as a density ratio. In practice, we only get the data, training data. So imagine if X is like image, Y is like text when we do multimodal learning. And another thing we have, remarked by Jason, this is the infinite dimensional function space SVD. So it could not be as simple as computing some matrix speed. But existing implementations have been discussed. If this is just the categorical data or binary data, then you can imagine we could do the empirical frequency and get the empirical label, empirical table, and do the matrix factorization. And a slightly more complicated case, there's one thing called alternating conditional expectation, which is an iterative algorithm proposed by Freeman in 1985. Because if you look at the operator version of the SVD, we get a fixed point solution that's like 2 lines of conditional expectation. But unfortunately, conditional expectation is not easy to compute. If you could compute conditional expectation, ideally you could compute any posterior. And we know all the classification models just to compute posterior. And early deep neural network-based models have been proposed since 2013, known as DCCA, which is Deep CCA. And the naive formulation proposed there doesn't have a good optimization. So it's restricted to relatively low dimensional feature space. So in the next few slides, I will discuss how we address the problem of computing this SVD. And to do that, first step is we slightly relax the problem because SVD is still hard. We have to satisfy all these constraints. Recall that they have to be uncorrelated, monotonically decaying, and have unit variance. And if you have read the literature in deep learning, deep neural network training, this is typically done by putting a lot of fancy regularization terms to guarantee they have some property. So instead of doing this constraint problem, we look at this unconstrained problem, that's the factorization. So we would like to factorize this I function as some fx and gy. The mathematical property would be very similar to the matrix case. We want to do something like this, matrix factorization. The difference is this matrix would be very long, infinitely long. And input, instead of this function as this matrix we will decompose, we never know the objective or the function we want to approximate. That's density ratio. Instead, we only get some sparse samples. Output would be features, and naturally we want to represent it as deep neural nets. Computation-wise, naive solution would be to minimize this difference or approximation error of this low-rank approximation. And this norm is defined in function space. So natural question is, if we can use this as our objective function, that's asking whether there's approximation error itself as a value loss. So it turns out we don't know the value of I, so this thing cannot be computed from data. But a slight change, if we consider the difference between the approximation error and this I squared, we call it this I is density ratio defined by data. So this can be treated as constant even we don't know that. Then the difference could be effectively computed from just data samples. Say we have n pairs of x and y. And for the simplest case, if f and g are both one-dimensional feature, we have only the cross term and the square term. And this would correspond to the covariance and variance of fx and gy.
Sorry, but I was a scalar variable, right? It is p of x, y.
Yes, it's scalar, exactly.
Yes, so then why is there a norm?
It's in function space. So it's like we can define how two functions are closed by taking that. Yeah, good point. So now we get this computation, and for general k-dimensional f and g, we could still do it. So the covariance and variance could be estimated by the integral average, and that gives us a value training loss, which is negative h-score. So by minimizing the negative h-score, which you can compute in 10 lines of code, you get an approach to solve the factorization. And suppose your network is good enough, then you are addressing the decomposition problem. For the sixth example, let's start with 101. So that's for general x and y. You would plug in two neural nets here, and this would be a module to compute its score just by plugging those 10 lines. And this address the factorization. The tallest example, MNIST, X would be the image, Y would be the label. And you can imagine what we can do is to plug in some convolutional neural nets or more fancier network as your F. And because Y is just the categorical, so one layer suffices if Y is one half encoded. And here's what we could do, convolutional neural nets, and this is what we can learn by using this H-score. And this is the feature visualized on training data, on testing data. So we can see that compared with probability, this H-score could better separate different classes. And theoretically, we could prove that is the optimal thing if you want to maximize between class distance and minimize within class distance. So that kind of gives an interpretation why this is a good thing. And I would like to briefly remark why that would happen, because we define the distance or approximation area in function space as some norm. So this kind of function space norm will translate back to the distance. So that's why we have some property in the distance space. And as you have already noticed, in this formulation, Y might not be restricted to a label because that's the wild correlation metric. We're just learning density ratio. That says we could do something more complicated. Say, if you want to have the so-called cross-domain retrieval task. So this task is you want to retrieve some image from the sketch. That is a data set you ask volunteers to sketch all this image. And the setting is given a sketch, you want to retrieve the real image that's containing the same thing. Say you could have like 10,000 candidates and ask for like top 100. And this is what we can get. We can show that compared with previous approach, we can get better performance. And it's remarkable that previous approach even used more information in the sense that they have either used generating model or label embedding or their combination. So that shows once we understand the information flow behind the model, it's possible to get some performance gain. And up to this moment, we have addressed how to use deep neural nets to solve the factorization problem. The only step we want to do is get back to the singular value decomposition as we promised before. And recall that mathematically, the low rank approximation and singular value decomposition are very similar in the sense that the rank K approximation will just be the sum of top K singular modes. So now we want to get back from the low rank approximation result to the singular modes. And if we think about the problem in the matrix case, it's never a problem because in the matrix case, we would like to do it in the reverse way. It's very easy to get the singular value decomposition. In NumPy, you just use one line and you get a singular value decomposition. And it's very easy to convert singular values, singular vector to low rank approximation. Because we just apply this, say we have top K, we want to get rank K approximation, then we just take the sum of top K modes. So that would be the best rank 1 approximation, rank 2, rank 3. And now what we need to do is to reverse this process. And the interesting thing, if we think about this thing in function space, we cannot do subtraction. So we want to add something, we can easily add something, but we cannot subtract. In the sense that you learn something as rank 2, then you subtract rank 1. It's no longer a product in general. Instead, we propose a novel architecture. And to see what's happening in this architecture, we will get to the synthesis case. So torch case, if we just want to learn the first singular mode, the first singular mode would just be the rank 1 approximation. So say we have F1, G1, one dimensional. Then we train the H-score, we get F1 G1. That is up to some scaling, reconstructing the first singular mode. So the trick thing happening starts from the second mode. If you just naively train some two-dimensional features, you will get the mixture of first mode and second mode because you only get the right subspace. Instead of doing that, we construct this net structure. So the second dimension F2 and G2 are fed to a different H-score by concatenating the first and second. So now you have a two-dimensional input to the second H-score. And if we check this optimal solution, we'll find that second H-score would like to have the sum of first two modes as a sum of first two singular modes.
Sorry. This is so cool. Just to confirm,
Yeah.
during this entire process, the only constraint we're putting on F and G is that they're rank K in the option space, right?
Actually, no constraint.
Okay.
Yeah, because if the skip neural nets have one dimensional output, that would be rank 1.
Oh, okay.
Yeah.
Do you freeze F1 and G1?
That's a good point. I will talk about it. Yeah. Mathematically, that's right, but in practice, it's optional. So interesting thing is if we think about the 2H score, there are two optimization things that's like separate procedure. But turns out the only common solution to make both H happy would be this one. If you have first mode as first singular mode, second mode as second singular mode. That says if we maximize the linear combination of 2H score, you get a solution. So you don't need to wait. But in practice, you can also do stop gradient. Then that serves the purpose as separate optimization routines. So continue this process, you will get top K singular modes. That's how we can drive neural net to solve the SVD problem for us. And if we check what we have done here, yes, we get something with automatic guarantee because we can show that this would be the only optimal solution. And this works for high dimensional data. Notably, if you want to deal with text or image, you just plug in the corresponding neural nets. Today, maybe transformer, tomorrow, maybe something. And that's unconstrained training, so it could be done very efficiently. So we might ask, what's the benefits? So definitely mathematically, we know that's a good thing. If we check this figure from the single value decomposition, we know that the optimal or the most important information will be concentrated on first few dimensions. That says, if we learn some 1,000 dimensional features, we know that top 500 will be more important than latter 500. So let's get back to the previous example. If we want to do cross-domain retrieval, now we can do something fancy. We can do it on truncated feature. In the sense that we have this comparison. By increasing the feature dimension, we see how the performance goes. So the curve in the middle would be if you do nothing, this is like unstructured features you get here. And if you go to the next result, what would happen is a top curve. So you can see that if you have structured dimensions by using only 1/4 of the dimension, you get almost the same result, same performance. And the adversarial setting, if you sweep from bottom, that's a list informative feature. Then you will find that the list quarter features are almost useless. That's almost as nothing. So that's what you can get from the structured features. And in practice, that gives you the optimal performance cost trade-off. Because in order to store all these vectors, say in the database, you need to pay the cost for computation, memory, and storage. Maybe just one moment, let me hide this. Yeah. So the key takeaway is we show that by defining this SVD, we could separate how we learn features from how we solving specific tasks. And this gives us a automatic way to use neural nets to operate this information. And you can plug in any off-the-shelf architectures and optimize this. And we might be asking whether this is a coincidence just because we did some tricks to design the thing so that it can work. Turns out we can have a more general function fixed space framework to extend this to arbitrary number of variables. So it can be, say, extend to conditional dependence when you have a third variable. And you can consider a sequence and use the neural nets to decompose this into different orders of Markov chains. And this would be the papers talking about the extension if you are interested. Any questions? Yeah.
why I'm saying that you separate feature learning from solving a task, because you still need this like XY couple.
Yeah.
So I mean, this seems pretty tight to doing regression.
I see. So you're asking, okay, so that's two levels. One level is what we can achieve currently is saying that I learn F star and G star. Say your task could be predict Y, or you could predict like I want to do a regression, but I want to predict some function of Y, some transformation of Y. In the sense that we learn the dependence, so they would be a special case. You just need to do linear adaptation. But in terms of if you want to do something with a different direction, like downstream task or third variable, then you have to take different dependence as your objective. Yeah. So that's the thing. We talk about some features that's good. We can learn it, which is quite good. But the next thing we need to think about is we have X and Y, and we talk about something as F star of X. But if we check the papers or like last year, we have like more than 10,000 papers on how we should learn features. So we have tons of different ways to learn features, and you have heard of all the principles, all the designs, and they all show that from some form, either theorems or empirical performance, showing that they are good. How could we understand the difference? That is, we have shown in a way that F star is good, but there must be some this F and that F. How should we put them into the same picture? So first thing is you have heard of some information related principle, like from early days Infomax and the information bottleneck starting from 1999, actually even earlier before that. And I don't need to introduce the definition of each information supposedly. So one thing we need to think about is, okay, before talking about how they are related to this, our representation learning framework, we need to know that misinformation has some challenge in practice. That is, first, this earpose, that means if we do a invariable transformation, X and Y, it won't change the value of misinformation. This invariance could be problematic in the sense that if we put that as our objective that says we are learning a large equivalent class, though that won't happen in practice for some reason. And second thing is computing misinformation is still very difficult as of today. If you check the publications on recent years, people are still talking about how we can more effectively learn misinformation, and even for toy data, it seems it's quite challenging. But if we forget about this challenge, we can, what we want to do is trying to understand if we could do the computation, how they are related to our features. So let's first look at Infomax, and a simple formulation of this is if you don't have any constraint, I just find some FNG. I want to maximize misinformation to FNG Y. And from data processing quality, the maximum value cannot go beyond X. So one thing you can check is if you do F star X and G star Y, they can achieve Infomax, and that's almost tautology. That's about the sufficiency, because F star X and G star Y are sufficient statistics. And we could even have a stronger condition saying that if your Fx and Gy achieve Infomax, that someone gives you a good feature from this principle. This happens if and only if your Fx are in the middle of X and F star X, and Gy is in the middle of Y and G star Y, in the sense that you have this Markov chain, in the sense that in order to achieve Infomax, you cannot contain less information than F star X and G star Y. And for our definition of minimum sufficiency, we know we must contain some possibly redundant information. So that's for Infomax. So if we want to draw a figure, and good thing here is we can draw a figure here. Then X will be here, F star X will be here, and we know that we have this Markov chain. That would be any Infomax variable. Suppose we could achieve that. And next, let's see the information bottleneck. And this is a principle dating back to 1999 and even earlier. So the same form appeared in 1980s, when people started information theory formulation called distributed hypothesis testing. And it got very popular just during the past 7 or 8 years, because 2017 people tried to apply it to illustrating the deep neural nets. So mathematically, what's happening is it want to find a description. So characterization means it not necessarily need to be a function of x, such that I want to minimize this information between u and x and maximize the information contains about y. And the popular form as proposed in Tishby's original paper is this Lagrangian. So you want to minimize this Lagrangian where beta is multiplier, and minimization is over all possible stochastic transformation or channels. So how this is related to f star x and g star y? One thing we could prove in a rather recent paper is that if you can solve this, arguably this is hard to solve for many data, even for simple Toish data. We can prove that optimal U must satisfy this markov chain. That says it has to be something that is describing f star x. So this would be the information bottleneck. And more interestingly, so we could show that if we replace x and y by the f star x and g star y, we'll get exactly the same trade-off. That says we could compute information bottleneck in a separable way by first learning the features and do the estimator in the feature space. And the benefit definitely because learning the feature is compressed in the original data, and we live in a smaller space. So if you imagine we are using some non-parametric approach, then the estimator could work better in the new space. So takeaway message is f star x and g star y achieve Infomax without computing the mutual information. And if we learn this, we could use this as an interface for computing the information bottleneck trade-off. So let's get to reality. That's a remark I would like to say here. We have talked about principles, and if you check all these papers, they are not using principles or not, at least not a single principle. So what's happening is in practice, all the learning algorithms have often been designed by combining different principles. I want to learn some features, then I could pose some constraints on distance, on similarity, or I could easily learn some non-negative features. Supposedly that's something good, and I could restrict the normal features. And that's a good thing. In practice, we have flexibility, but it's bad thing for theoretical understanding. That says we have to face tons of different designs, as they can be easily combined by taking weighted sum, that's regularization. And in practice, that would involve hyperparameter tuning. And we ask the question, given there are so many possibilities in designing the feature learning algorithms, how are the features related? So a good thing is now we have an anchor point. We know we have something called f star, and for some reason it's optimal in information computation sense. So our hope is they could be related in some sense. To do this, we first have abstraction, what's happening in practical algorithm. So we can abstract a large class of algorithm as some loss minimization. You'll have a loss L, a functional defined on feature f and g, and you are dealing with a pair of data. And I would like to mention a few examples, say, supervised learning, X would be data, Y would be label, and self-supervised learning or contractible learning typically have a pair of augmented data from the same image or text. Multimodal learning, say clip, you have image and text feed. And several common examples of loss L is like quadratic loss and cross entropy. You can think of this would be you operate something on fx and gy. In the H score, we just introduced as another example. So you can see that they seem to be very different. How could they be related? And you could consider all the transformations on top of that. So this is what's happening in recent years. People want to understand how the different representations could be related, and there are some empirical approaches, say like CKA proposed, and you could see a lot of fancy figures on this, and unfortunately they don't have consistent results in the sense that some papers say they are very similar, some papers say they are not very similar. So that's not a good way to think about it, because we know even we train the same network 10 times, we will get 10 different results after some symmetry. So instead, we want to look for this problem from a theoretical perspective. What we want to do is, instead of thinking of general L, we restrict ourselves to a specific form of L. That is, we call D loss. So we consider the loss taking the form that's expectation of some gamma on top of fx and g. And we put some restrictions. So expectation is over either joint distribution or independent samples. And if you are familiar with contextual learning, this would be positive and negative samples. And we restrict this gamma, which is a scalar function, taking two vectors as input. We suppose this gamma is convex with respect to each argument. That's by fixing the other, it has to be convex. And this is the basic form. And now we allow the family to contain all monotonic transformation of different basic forms. So if you like, you could put exponential outside this. And for different gamma, you can take the weighted sum as a linear mixture of them. And we can easily identify all the previous examples, quadratic loss, which is quadratic function we like. Cost entity, if you check that, take the log, take expectation. First term would be bilinear, and second term would be convex with respect to each argument. That's log sum exponential. Hinge loss is not another example, and negative H score, if you recall that first term is bilinear, second term is some covariance. So these are all examples of D loss, and why this D loss would be special. One thing we could prove as a key result I want to talk about today. Okay, before that, these are examples in self-supervised learning and multimodal embedding models, because cross-sensitivity has been used anywhere, everywhere. So like from the very early non-parametric instance discrimination to simply to clip, they all use some variance of cross-sensitivity. So they are all special cases of D loss. And H-score was developed independently in contextual learning, also known as spectral contractible loss. So this shows a lot of examples are special cases, and even if you take their combination or like some regularization, as I will show here. So that's a key theorem I would like to discuss. For each D loss, we could prove that the optimal solution will take this form. That is, you minimize the loss, but eventually your optimal F will take the form as some transformation phi on top of F star, and G would be some psi on top of G star. So if we think about what this theorem says, it has three different components. To the left, F star, G star are what we just talked about. It's defined as factorizing the density ratio. So it has nothing to do with the specific form of L. This is some information we'd like to learn. And to the right, this loss is how we do the practical computation. That's by minimizing loss. You could run gradient descent. And how this information and the computation are combined are through this composition form, if you think about it. They are said to be the most natural form in deep neural nets. Because what we like to do after train some model, you would add 3 MLT layer on top of this and adapt this to a different model. So this adaptation happening a lot in practical usage. So the implications are, first, learned features cannot contain more information than star and G star because they are some transformations. It's like further processing. And second, for the large class of loss, we could lead to highly related features. So that's just why we could do feature adaptations, even we have tons of designs on one side, and arguably the useful information are not that much. Third thing is, if we want to do separable learning, here we can do by first learning this F star and G star, then fix this because phi and psi could be learned on top of F star and G star. And that would be useful if you have 10 different losses or even many of the losses taking the same form. Then we just need to learn F star and G star once, and notably then the hardest part, then adapting them. So there are more examples. If we do something seemingly very different, say in the early work of estimating matrix information, we could consider the versional bound of matrix information taking this form, and now you can easily see the first term is bilinear, second term is convex. And if we apply regularization as weighted sum or like taking the norm into consideration, and you have this lambda 1 plus this lambda 2 plus this lambda 3, that's another example. Even you do something that's not very similar, like you put constraints. If you just project your feature into this norm board, or you put non-negative constraints, because they are convex constraints. So they are all special examples of this DLOS. So an interesting question is, we have this very special form, which seems not very trivial. And if that's the case, why didn't we notice that? Or in which case we could notice that? So one thing I would like to mention is that if imagine this is a training result from some training 100-layer network, you can never expect like you just cut in the middle and find one layer gives you F star, because this is a computation result, and you cannot reverse it saying that there exists some intermediate layer that gives you F star. But there's one special case, that is if your F star X is simple enough, say your F star X only takes 10 possible values, what would happen is no matter how you transform it, it cannot take more than 10 values. And that would happen in a special case if your Y is a determinate function of X, so that's a strict dependence case. So what's happening is, so why this would happen? Because you never want same image to have two labels, that's ambiguity. So in classification data set, if you look at training data, your label is always a determinate function of your image. In this case, because we have talked about this F star as minimum sufficient statistics, so it had to contain all information about Y, but Y itself is a determinate function of X. So in this case, F star has also to be a determinate function of Y. And as a consequence, F as a transformation of F star must also be a function of Y. So in CETA 10, Y only have 10 values. What's happening? If you overtrain the classifier, you will find that the feature will cluster according to Y values, in the sense that you will find that the feature are 10 clouds or 10 points. And that was known as neural collapse, has been studied like in the past 5 or 6 years. So I would like to remark that though most previous work studying neural collapse from optimization perspective, our characterization shows that this is not only about optimization, because the statistical property of this data is so special, so you have to learn something like this. And key takeaway is we have a large class of features that can be learned from star and G star. That gives us another example of separable learning. And this gives us a unified interpretation of how different features could be similar, and how the feature adaptation could work just like in the era of foundation models. And this gives a statistical interpretation of neural collapse phenomenon. So any questions up to this moment? Yeah, good. I would quickly go through some applications and show something. So if we look back, what we have introduced is kind of how we can guide deep neural nets by information. So instead of using deep neural nets as a black box, as data fitting, we can now use it as an interpretable computation module beyond simply fitting the data. As I will briefly talk about, we can easily use this to solve other action problems or PDEs. And instead of using this as a theoretical way to solve a problem, we can now use this as a reliable module to solve some engineering problems to cover domain knowledge or system model. And because we know what's happening behind this training, we can also use this as a tool to debug existing data-driven solutions, because we know what we can expect from training. So here are 3 quick examples. And first one, computation, and definitely go to the very fundamental stuff. That's about if we want to understand nature, then that's Schrödinger Equation. So before talking about this, just know 2 things. One is Schrödinger Equation is an eigenproblem, and we would like to argue why we need deep neural nets to solve this problem. Why this would be a high-dimensional problem. So if we think about a system of n electrons, what's happening is to capture the system, you need 3 n dimensions. So say 10 electrons, not too much, 30 dimensions. why 3 dimensions are a big deal. If we think about any numerical approach, say finite elements, what's the practice? It's like you draw 10 grids on each dimension, then that's 10 to the 30, so you fail. And if we get back to think about how neural nets do the thing, it's like 3-dimensional function. That's like a neural net with 30 output neurons, nothing. So that suggests we could use a neural net to solve the Schrödinger equation. And we demonstrate the easiest example because for a few cases, we know an analytical solution. And notably, the easiest one is 2-dimensional case. And why we could solve this, because I have introduced the approach to solve the single value combination. And we call it eigen decomposition if the operator is symmetric, is the same as single value decomposition. So we could just plug in by replacing the I function as an operator H hat. So here's what we can get. And this is from the approach. We call it neural SVD. And we can see that for this 2-dimensional problem, we could get the wave function almost the same as ground truth. And this is orthogonality as any check. And in contrast, previous approach either failed to compute high order modes, or they got something that's very out from the ground truth. So that's the interesting thing I like to remark here. Recall that we didn't do any explicit regularization or post-processing, but we can get the orthogonality result. That's just from our theoretical guarantees. The second example is a bit classical engineering problem. That is, I don't know if anyone from here are doing communication, but this is a very classical example that's called simple detection. We have like 2 users, say x1, so both x1 and x2 are complex numbers, so we can realize this on complex plane. So x1 sends 2 possible messages, either 0 or 1. That's like next to 1 or 1, and x2 has 16 possible values. We like to detect x1 based on received signal, and here h1, h2 are the channel gain, and in live communication, these are random variables because depending on distance, depending on the environment. So the task is to detect whether you are from a red cloud or a blue cloud based on received y. That's any point on this plane. And you also know the channel gain h1, h2. Why this would be difficult? So the difficulty is not just do a binary classification as shown here. The difficulty comes from the fact that h1, h2 could change over time. So instead of drawing one decision boundary, you have to draw many of them. So you have to have decision adapt to the channel change. And our solution would be learn the conditional dependence between your input and output conditional on the channel gain h. Though I didn't talk about how we deal with 3 variables, but here's what we learned. So that's the easy case. If these 2 clouds are well separated, that's how our neural nets learn. So that's like sanity check. But as we will see, even we go into more complicated nonlinear case, our neural network can still adapt to the solution. And in this near-term paper, I discussed how to incorporate system model and other design considerations to solve this engineering problem. And the second case or third case, you can see how the network could adapt to change. So what's good about this problem, though this is notably not a very high number problem, but we know the analytical model, that means we could do quantitative performance, and here's the beta rate, compared with optimal one, which is based on math, that achieves the lowest error. And we can see that under different conditions, it can closely match the performance of the math. And notably, naive linear decision would fail if your fitting coefficient is too bad. So that's the second example. And then quickly go through the third one, how we can use this to boost existing solutions. That's an example called intrusion detection, which is basically you want to detect good network traffic from bad. You want to detect bad one from normal ones. And challenges, you don't have much labels, because if anyone want to hack the system, they have to be innovative, so they are not in your data set. So basically, we use H-score as a method, because if we think about the problem is binary classification, and the only purpose is trying to drag this file far apart, and we know H-score is the optimal solution. So based on the existing contractive learning approach, we can use H-score to further fine-tune performance And that's something we just published on the MobiHawk. So that's some examples. And if we think what we can do as future directions, one thing I didn't talk about is how we can extend this back to intermediate layers. That's arguably more complicated. And instead of just looking at the optimal solution, we could also think about how we learn the features. And in terms of application, because now we have such a recipe, we could easily extend this to other engineering and scientific computations. So in short, we have demonstrated somehow how we think about the interaction between information and computation, and because I'm in the science building today, so let's look at another example. There's a workshop on large language model, though I'm not very large language model, but let's think about simple text generation. So this is a problem, toyish, actually it's a story. Given the title and the text, you want to generate some text. 2025, we are not very surprised of anything I will show here. So first I will show you there's some text, it's not too bad. But the real story is not I use some Gemini or Cloud or something to generate this. If I told you this is from GPT, that's not surprising at all. The surprise fact is this was generated from 1948 by notably Shannon. So how Shannon did this? Without the computation or with a different form of computation. Shannon has some volunteers, human volunteers, and he did the game as follows. He asked each volunteer to fill the fourth word for any given and for given 3 last words. And you would ask why this would be titled. I mean, now this is very standard prompt. So Shannon discovered that without the title, because you only see the context length of 3, you would write something nonsense. So this one read very well. So this title would be provided to every volunteer. So every volunteer would see 3 words as 3 last words and the title and write the following. And you can see they have some concise meaning. And here's what we can, this is the original piece. By the way, that's from MIT's library special collection of Shannon's writing. So yeah, I'm fortunate enough to get rid of the original piece, and this is some other thing generated. And interesting is Shannon even did a comparison. It's like he randomly mixed some human written text, and you can see that they are hard to distinguish even then. And the story continues. So this model would be the early phase of text generation, and now it's known as the n-gram model. So if you given 3 generate 4, that would be 4 gram. And 6 decades later, so recall this is 1948. 6 decades later, we had some computation in some 2000. What we did, Google did this n-gram model 2006, and by processing 1 trillion words, they can compute n-gram models up to 5 grams. And back then, they store all the n-gram data. So how it looks like, it's like this, say 4 grams. That would say the certain combination, specific combination of this appears 92 times, this 99 times, as so on and so forth. So back then, this table would require 6 DVDs to store. And that's 2006. And what's happening today, we all know. So that just shows, in order to get the same piece of information, all the information about the structure of text, we can have different computation, and that's somehow with improvement in computation, we can see different forms of interaction. And an interesting fact is even this device called computer was redefined by this electronic form. So the original meaning of computer, you can see, are human, not the electronic device. So notably, deep learning gives us a different form of computation. And in that sense, the understanding of interaction between information and computation could provide us more effective computation, gives us a better starting point to rethink what kind of computation we will need. And it possibly suggests new form of interaction between the information and computation. Maybe there will be some feedback beyond backpropagation. So I'd like to conclude my talk here, and with that, I would like to thank all my collaborators to give me the inspirations and help me with all these applications. So thank you all for coming. I'm happy to take any questions here. Yeah.
Any, I guess, like any transformation of I function can also be actually.
Yeah.
And that's like, let's say that two and G2 are actually transformation of function.
Yeah.
I guess they are all equivalent to the F side and G side.
Up to okay, so we proved one proposition that says that if the transformation, because you are operating on I function, that's a scalar, right? If a transformation is monotonic, say, so it doesn't lose information, then the kind of factorization or single value combination gives you something, and that's up to an invertible transformation. So information-wise, they are equivalent. Yeah.
So is there a way to how to compare it? Well, I guess this is a way to help the comparison of your H
score and other possible variants. Yeah, exactly.
How do you compare this different representation as
That's a very good point, and notably one very popular one is point-wise information if you take the log function. So if you factorize in the log, and you will get something, and that will be the solution you get from Infomax, for example. And there are at least two perspectives to think about this. One is just thinking about this as a way to factorize or to parameterize the density ratio. So on top, we can think of this as density ratio estimation. And the short answer is, I think this is still a very active research area starting all these different forms. But the mathematical connection have not been discussed a lot yet. So I think that would be like something we have to consider in terms of how efficient the practical implementation would be. And the one interesting thing is if we replace this density ratio by other transformation, this induced H-score-like term will not be easily computable by the same means, because you can feel that's like some kind of trick, so we can cancel out this PXQY to make this computable. But there are other approaches to do the same thing, like you just work on a small batch and construct samples. Yeah, I think there's no short answer to this question.
So in practice, I guess people are still using the exponential.
Yeah. That's a good point. But my feeling is it's hard to claim which one is more or computationally more fundamental, because they are all related to what kind of optimizer, what kind of architecture you are choosing. And it might be some kind of bias in terms of if everyone is using the exponential form, then they might tune their hyperparameter and optimize their architecture towards that thing. That's like a similar question, or a simplified question would be whether Tishby would be the only thing you want to pursue. I think there are different arguments. Okay. Or you want to have a follow-up? Yeah. 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 H-score is exactly chi-square loss. Yeah. Chi-square. Okay. Yeah. I see. Yeah. Okay. Yeah, that's interesting. I know it's recorded, but somehow that aligns with our experience. So we were suspecting maybe there's some implementation bias, because the optimizer or architecture we are using have been verified, for all those applications. You found they are just so good, but most applications were developed just devoted to, this log or cross entropy case. Yeah, so there's a discrepancy between the theoretical benefits and the practical implementations. Yeah, but that's a very good point. Yeah.
If you wanted to, I think you alluded to this in your talk, but if you were interested in like transfer learning applications.
Yeah, you have to introduce a third variable. And so you can imagine in a rough sense, if you could have a F star for the source task and F star for the target task. And in terms of how many samples you have for the transfer, then you would have different. So the implicit assumption is if you can transfer very well, then the two feature space must be well.
Okay, that's the isomorphic.
Somehow.
Okay.
Yeah.
Thank you.
Yeah.
So you were talking about intermediate layer.
Yeah, as a promising future direction.
Yeah, you said a very vague way. What ideas do you have that? Because I know one of the things that a lot of people are working on in terms of intermediate layer representation, SAEs, mechanistic interpretability stuff, where you're kind of taking this compressed representation and trying to decode it early to kind of see what's inside or something, right? So, yeah, what are you thinking about?
I think a short remark I would say is this highly depends on optimization. Right. It's like if we do end-to-end training, it's like we encourage everyone to be, adapting themselves so we can get better loss. But imagine an adversarial case. Yes, if I just restrict different layers to have very different learning rates, then you can imagine you will observe very different phenomena. So in short, what you can observe as a final result would be somehow a mixture of training and your optimization. Yeah, but so some big way to summarize this as some inductive bias. And I think in order to have a more theoretical way to talk about this, you have to put assumptions. But mathematically, there would be something different you could think about, like this is SVD. SVD is about eigenfunction, eigenvector. And in matrix case, we have power method. So if we think about that way, maybe this would give some different construction. It's like we know how to use iterative algorithms to compute, eigenfunctions. Yeah, but this still has some discrepancy. We can see it.
One question is, you can imagine now there are multiple layers which you learn in structures. Then, like for example, in that setting, for example, how does did you analyze how this future learning steps change? So, for example, imagine the UNet activities. You learn that the anxieties. So like you can multiply the steps. So did you try to get one of these different intermediate layers? Wow.
So you're asking about intermediate feature and interaction with architecture. Yeah, so architecture is like the skeleton you put or the constraint you put on feature space. So it's like you can think of all this are like unconstrained results. But somehow there is more complicated interaction in terms of the architecture. That's like a constraint problem.
Is it really a constraint though? Like these things are all like universal function approximators and right? Like
that I would say there's a discrepancy between you can express them versus you can learn them. So the latter express optimization, even for this scale. And this way decay would force you to have some minimum norm constraint. So that's something. Yeah. And guess the reason this could generalize well, which I didn't talk about. Yes, you have some kind of interpolation. And it seems to be as each architecture defines some kind of kernel function. Yeah. But that's a very good direction to look at.
I think this might be related to what you just said, but because you're learning in the function space,
Yeah,
and you're only taking the top few
yeah,
inputs, you're robust to noise. That's
exactly.
right. Okay.
Yeah.
Thank you so much.
Thank you. Yeah, we could keep more questions offline if you want.